Hey everybody, Mr. Lake here with another chemistry lecture video. Today, we're talking about the laws of conservation of mass and energy. Maybe you've heard of these before, maybe not. Either way, let's get into it. We're going to tackle these from a chemistry perspective. So first of all, you may have heard this before, but energy cannot be created or destroyed. Energy can only change form. So there's a certain amount of energy in the universe. There's never going to be any more or any less. And that energy just kind of goes through cycles of changing from one form to another. Kind of interesting to think about. It's kind of a beautiful thing to think about. Now, I believe that there is some experimental kind of theoretical physics that explains how possibly energy could be created or destroyed, like a quantum level. But for all intents and purposes, energy can't be created or destroyed. It's always conserved. It just changes from one form to another. And even though most people in one of their high school or middle school classes has learned this phrase, it's really easy to forget because sometimes we see examples like giant explosions where it's hard to believe that energy was conserved. Because what that means is that in the case of like a nuclear blast like this, it's releasing a ton of energy, right? There's like this giant shock wave. There's this giant flame. There's this big explosion. There's a lot of sound. Like there's so much energy that is released by a blast like this. It's hard to believe that all that energy was just there the whole time. In that bomb or explosive that was there before, all the energy was there, just in a different form. And it just got changed into a few different forms and released all at once to create this blast. But energy cannot be created or destroyed. Similarly, mass cannot be created or destroyed. And you may have heard of this as well. You can't make new stuff. There's a certain amount of stuff in the universe, and it can be recycled and switch from one form to another. But there's only so much stuff. And actually, the Earth is a great example of this as well. Like the Earth is only so big, and the Earth only weighs so much. And with the exception of maybe like some, rocks falling from space and hitting the Earth, that's like the only example of mass being added to the Earth. Otherwise, the Earth's mass stays the same. And the Earth's mass includes us and the buildings that we build and the food that we grow and eat and the garbage that we create, and all of that is part of the Earth's mass. And the mass is not changing. So it's simply that mass and matter get changed from one form to another form. And then eventually, things decompose or things get recycled or the water cycle, takes the water and evaporates it and it rains back down. Everything is a cycle and everything recycles back. And the matter that exists on Earth has probably gone through many, many different forms throughout the billions of years that it's been here. And the most current form is just you and me and what's out there right now. It's kind of a weird thing to think about. So, from a chemistry perspective, another way I want you to think about the law of conservation of mass is that in a chemical reaction, the mass of the reactants is always equal to the mass of the products of the reaction. Remember, reactants are the things that go into the reaction. The products are the things that are produced or that come out of the reaction. So the mass of what goes into a reaction is always equal to the mass of what comes out. If I was you, I would probably write this down, but I would especially write down this equation because this is kind of the first equation that we're going to use in an applicable way. Very simple equation, but we are going to use it. It's also really important conceptually to remember that mass cannot be created, even though in a situation like the one you're seeing in this GIF over to the side, it kind of looks like mass is being created because you're taking, a couple small cups of liquid and combining them together, and boom, you've got this giant mass of foam. But the mass of what was added is exactly the same as the mass of what was created. It's an incontrovertible law of happenings. Mass cannot be created or destroyed. So that mass of that foam is exactly equal to the mass of the liquid that was drawn together. Although probably some gases and things are being released in this situation, so that might not be entirely true. But if anything, that giant pile of foam is actually less mass than the liquids that were combined together. Now, before we move on, I want to point out what I don't like about this GIF. It's cute and all that, but maybe you've also identified some things that are wrong with this. This person performing this experiment, demonstration, whatever you want to call it, is not wearing any safety precaution or safety protective equipment at all. And you should really be doing it anytime you're doing anything that could have the potential to, splash or spark or anything like that. But especially when you're doing a demonstration where the intention is for it to create this big, like effect that is inherently unpredictable. You don't know exactly where that foam's going to land or anything like that. I mean, this is an example where this person should absolutely be wearing eye protection at the very least. If I were doing this, and I have done this demonstration, I would wear eye protection and a face shield. I would also wear gloves, and I would wear either a lab coat or an apron, because that foam, you might be able to tell at the end of the video, it's steaming. That foam is very, very hot. This is a very exothermic reaction. And so if that foam landed on your skin, um, it would likely be uncomfortable. It may actually cause damage. And also, there's not like, it's not just soapy bubbles. Like, you use chemicals in this equation, and there's some potassium there's likely some potassium containing chemicals and other things in that foam that you don't want to get on your hands or your skin. You don't want to get it on your clothes. It'll stain your clothes. You definitely don't want to get it on your face or in your eyes or in your mouth or nose. And all of those things are potentially could have happened to this person. So wear your goggles, kids. Don't be this fool. This is a chemistry failure. Saying it like it is. Mr. Lake. All right, let's move on. Okay. Let's do some example problems to kind of walk through how this mathematical implementation of the law of conservation of mass is helpful to us. So let's imagine that we've got a friend, Gerald, who is a bit of a daredevil, or you could say a bit of a uh, troublemaker. I don't know. And he gets his hands on 20 pounds of dynamite somehow. Let's not even talk about how that happened. That's a little bit concerning. By the way, this is a fictional situation. And he explodes it in his backyard. So, what's going on in the case of dynamite is that you've got nitroglycerin. Dynamite is basically sawdust soaked in nitroglycerin and then encased in something. So, you've got nitroglycerin, which that is the chemical equation for nitroglycerin. And it's going to react with oxygen in the air, and it's going to produce carbon dioxide, water, and nitrogen gas, and maybe some other things as well. And of course, this isn't really part of the chemical equation, but there's going to be some debris left over, things that didn't combust and become gases. We haven't covered exactly how to write chemical equations, but I'm going to start showing you chemical equations just so you can get used to seeing them, even though I wouldn't expect you to be able to write what I just wrote without any guidance at this point. Someday soon, you will be able to, but not quite yet. So this is what's going on, right? And we know that there's 20 pounds of this to start with. There's oxygen in the atmosphere. There's kind of an infinite amount. Well, not technically, but in this case, the oxygen is our excess reactant. There's just a lot of oxygen in the atmosphere, enough to react with. So we don't really need to worry about that. And the products are all gases, but we know that there's 4.97 pounds of debris left over at the end. By the way, these are numbers that I made up. All right, so this isn't a perfectly balanced chemical reaction. These are numbers that I made up. So there's a little note down here that's hidden by my video feed at the moment. It's not all made up, but the numbers are. So we've got 20 pounds of reactants I'm going to kind of simplify this. Mass of reactants is always equal to the mass of products. We've got 20 pounds of reactants, essentially. And then we've got products. Oh man, I got to disappear. Bye. We've got some products, and we have 4.97 pounds of debris. So if we subtract the amount of debris that was made from the initial mass of the nitroglycerin, or the dynamite, I should say, then we get that that's 15.03, right? 15.03 pounds of stuff was released into the atmosphere, combination of carbon dioxide, water, and nitrogen. And eventually someday we might be able to break it down and tell exactly how much of each of those things there are based on their, molar ratios and that sort of thing, but we haven't gotten there yet. So this explosion released about 15 pounds of stuff into the atmosphere. That's too bad. Let's do another one. And I'm actually going to pause talking for about 5 seconds, so please pause the video and try this one on your own. Press play when you're done. I hope you pause the video and try this on your own. But let's talk about what happens when you burn firewood. And again, my numbers aren't exact here, but this is an example that you may be familiar with, especially this year after, living with under the umbrella of COVID for a long time. The very limited personal um, socializing that I've done has pretty much looked like this. It's been outside with people very distanced away from one another, sometimes around a campfire. So we probably had a lot of campfires in the last year, and maybe you have too. But when wood burns, again, first of all, law of conservation of energy, the flames that are produced when you burn wood, that energy was there the whole time. It's kind of poetic. It's like the wood contained the flame the whole time and you just let it out. But that energy was there the whole time. And what's going on is that the carbon-rich compounds in the wood are reacting with oxygen in the air, burning. That creates heat and light, which is the flame. And then carbon dioxide and water are produced as well. So we've got the wood burning with oxygen, and it's producing carbon dioxide and water. We start with 25 pounds of wood. And we're left with some amount of like gas, stuff that was released into the atmosphere, carbon dioxide and water, right? And 3 pounds of ash. So, how much of these gases, carbon dioxide and water, were released into the atmosphere? Subtract 3 from both sides. We get that 22 pounds of stuff was released into the atmosphere. So, this is not to guilt anybody or anything. I have plenty of, like I said, plenty of campfires and things like that. But just remember that when you burn stuff, and you start with a big pile of wood and you're left with just a little bit of ash at the end, all the rest of that material, it didn't just disappear, it's now gas in the atmosphere. And the unfortunate thing is that those gases, both carbon dioxide and water vapor, are greenhouse gases and they contribute to global warming and that kind of thing. Also, did you know that fire makes water? Because it does. Now you know. All right. Practice problem number 3. Again, pause the video, start it when you're done. Hope you paused it because I'm going to explain how this works right now. So, Antoine Lavoisier, very famous scientist, not a name that everybody knows at this point, but if you've taken a chemistry class or you're taking a chemistry class right now, you're probably going to hear his name. He was one of the first people to demonstrate this law of conservation of mass. And the way that he did it is he took 10.00 grams of mercury. So he did this experiment where he took mercury oxide and he decomposed it, meaning that he heated it up until it kind of fell apart into different parts, decomposed it into just mercury and oxygen. He started with 10.00 grams of mercury exactly, and at the end, he was left with 9.26 grams of liquid mercury. By the way, I would not do this personally, not unless I had very, very extensive personal protection. Heating up a mercury powder until it releases gas and becomes liquid mercury doesn't sound like a super safe thing to do. But I guess Antoine either didn't know or was perfectly safe about it or didn't care. Who knows? So he heated up this 10.00 grams and was left with 9.26 grams of liquid at the end. But he was also able to capture the oxygen and prove that there wasn't just this much mass really. Some mass wasn't just destroyed, it just changed form into oxygen gas. So how much did the oxygen gas weigh that he was able to collect? Well, if mass of reactants equals mass of products, it means 10.00 grams, the mass of the products, reactants, is going to equal 9.26 grams plus the mass of the oxygen. So if we subtract 9.26 grams from both sides, then we should get the mass of oxygen is equal to 0.74 grams. Okay, one more example. Again, pause the video, do this yourself. And I hope you pause the video because now I'm going to explain. If you can't tell, I'm late for something and I got to finish this video quickly. So this is a little bit of a different take on what's going on. We've got a catalytic converter, and in the catalytic converter, what's going to happen is that carbon monoxide is going to react with oxygen to create carbon dioxide. So this is a synthesis reaction, a little bit different than what we've seen before, where one thing creates multiple products. Now we've got multiple things creating one product. So let's say that you don't know how much carbon monoxide a car is producing, but you know that 16 grams of oxygen was used and 44 grams of carbon dioxide was produced. So the question is, how much carbon monoxide was there to begin with? Well, we know that mass of reactants is always equal to mass of products. So we've got mass of carbon monoxide, which we don't know, plus 16 grams of oxygen is going to be equal to the 44 grams of the carbon dioxide produced. So the variables are in different places, but the process for solving this is exactly the same. We can just subtract 16 from both sides, and we get that the mass of carbon monoxide is 28 grams. So there was 28 grams of carbon monoxide produced by the car initially. All right, I got to go. So until next time, take care, everybody. Have a great day, and I'll see you in the next video.